Hello. Today we want to have a look at a quite nice sensor, the BNO055. This is a 9-axis sensor, so an IMU, how you find it like in a drone or in a game controller or in your mobile phone. And we want to have a short look into the technical details and how we program it with Zephyr. And here we see why it's necessary that we understand how such a sensor is working and that we are able to program it by ourselves, because there is no driver available for Zephyr. At least I didn't find one in the Zephyr folder. So let's have a look at the sensor itself. It's a sensor from the company Bosch. It consists on a Atmel microcontroller, former Atmel, now it's microchip. It's inside a SAM20D ARM Cortex M0 Plus microcontroller, so it's already quite powerful microcontroller inside. Has 256 kilobyte flash and 32 kilobyte RAM. And inside this chip we find accelerometer, a gyroscope and a magnetometer. And there is also a built-in fusion library, so we don't get only the raw data if we want, we get already like the Euler angles and quaternions, and we will read out later quaternions because they're quite nice to use and avoid a lot of disadvantage from the Euler angles. So the fusion library, which is already inside in the microcontroller, so this is a smart sensor if you call it like this. There's already calibration inside. We can get the raw data, the Euler angles, a quaternion, or there are different modi which we can use, like for an IMU, a compass, or we get just all values, 9 direction of freedom. It's easy to use, but we don't know the algorithms they're using. Yeah? So it's all stored inside, and we have to trust that the values are good. Yeah. Here you see how I made it with our developer kit. The problem with this sensor is that you cannot connect it with cable, of course, because we don't get the direction out of it when it's flying around like anything. And when we want to measure the position of our boards, then we have to add a bridge. So I design here a bridge. I will put also Gerber files for download if someone want to use this kind of bridge. Yeah. And at the top I'm using the Breakout board from Adafruit. Here, before we start, we have to take a look in the datasheet how to program it, or in another library for an example or something. What we are doing is to build a finite state machine. We are using Zephyr again, the framework for finite state machine. And the process is we read out first the device IDs, that we are knowing that the device is reacting, that the connection is okay. Especially as this device can have multiple IP addresses, I²C addresses, and that we choose the right one. Then we are setting the operation mode to configurations, that we change a few configurations at the beginning. Especially the page ID actually at the beginning is already at page 0. We make it just for safety. There are a lot of registers, and we are using the page 0 mostly all the time. There are only a few things which you can configure into the page 1, but for safety we are setting the page ID before, and then we are setting some external crystal from the board that it's more accurate. The Adafruit board has an external crystal on it. When we say that it should use it. Then we are setting the operation mode. We are using the end-of mode, 9 degree of freedom. So we're seeing here always which address register we are writing, and then we are using the mode, operation mode, end-of. Then we are reading out the quaternions. We are setting the address to the first quaternion. Quaternions are 4 values, so x, no, it starts with y, x, y, c, and we're reading out for this 8 bytes because it has always a lower byte and an upper byte, least significant byte and most significant byte. And then when this is done, we get here integer values. You need to calculate from this out the quaternions. These are always values between 0 and 1 are float. We are using for this, if we are doing this later in another program, we make it in Python, that we don't have to handle here float values. If it's not calibrated, so then we store before a flag that it's not calibrated, and if it's not calibrated, then we are going into the read calibrate register. So we are reading the 1 byte, and in this 1 byte there are 4 values, all between 0 and 3. And only when everything is set to 3, then the sensor is registered. So there's one for the gyroscope, one for the accelerometer, one for the magnetometer, and one system calibration. I don't know actually what this makes. The accelerometer is the most difficult to calibrate. And if it's already calibrated, if not, we are going back. When we are finishing reading out, we are going back 50 milliseconds. So it's that we're getting 20 samples per second, so 20 hertz. This is quite accurate for simulations, that you have a quite smooth possibility to show the position of the board. And when it's already calibrated one time, we don't have to go in the read calibration registers, and we are just reading out all the time the quaternions. So why we are using quaternions here? We are don't need any rotation matrix. These are quite complicated to calculate with quaternions. You can make less calculation operation system. The most important thing is that Euler winkel can cause a gimbal lock, and also when you are near over 45 degrees and it's not so smooth anymore. And quaternion is just how to say, a mathematical expression for a position into 3 dimension. And you know it maybe from complex number, when you're having 2 vectors and they are multiplicated, then we're getting the angle between the sum from this vectors. What are quaternions? It's a generalization of the complex numbers, so we don't have only one imaginary part, we're having 3 there. We are writing this into a quadruple, and the rule is that E square is equal to G square, is equal to K square, and also this is equal to E multiplied with J multiplied with K, and this is -1. There are few rules which are followed, and this is actually some mathematics behind the quaternions. We take a look at the datasheet. We have always go deeper when we are programming a sensor like this into the datasheet. And you're seeing here, we're having here the register. Here is map 1, which is for us not really important, as a page 1. And this is from page 0. And the address 0 has here, for example, the chip ID, which we read out to checking if the sensor is working. And you see here, you're having here quaternions, the quaternion data starting at register 20. And you have here a lot other register for configuration and so on. And how we are programming this. So like the sensors before, we are defining a lot of macros. Here you're seeing the address of our sensor. It's 28 for our sensor in this case. And you're seeing here the operation modus. When you want to configure something, you're going into 0. When you are going into nRF modus, you're going in 0C. There are also a lot of power modus for save energy. We are not using this here. We're seeing here the chip ID address, the page ID address for changing the page ID. Then the quaternion, where they are starting, and where we read out 8 byte. There's also a temperature sensor on the BNO. You could also read out this, but we are not doing this. Here you're seeing the calibration register. It's on 3.5, and where we're setting the operation mode. Here is this trigger address. This is for setting the clock. I defined here also for LEDs. The LEDs are for the calibration part. At the beginning they are on, and when everything is sensory, I make them off, so when the sensor is calibrated. The interval, like I said, 50 milliseconds. The arrow sleep actually I don't use in this case. And we are using our SMF state machine. Yeah? So don't forget, there was another video where it's explained. Yeah, we have to include the header file, and also in the input files we have to activate the SMF. Yeah? Also, of course, I²C. And for C print floating point, but I think I also don't need it for this example. Then I initialize the LEDs directly. Here's the variable, the spec variable. Here our states, yeah, from the state machine, which we had here before. I make 1, 2, 3, 4, 5, 6, 7 states. And they are all here. Actually, I added here an output state for printing it out. But I think I don't use it, yeah, so I can delete it. This was just the plan before. No output state. So, we have our object which we need, but we are not using. Then I have here a variable for sleep, which I set since time between the states. A write buffer and a read buffer. Since we are reading out maximum 8 bytes, so it has a size of 8. Here I make a data structure for the BNO055 data, where I store the device ID, the calibration for the magnetometer, accelerometer and gyroscope, and for the system. Then a variable if the sensor is calibrated. And I initialize this then at the beginning with false. And also the calculated quaternions, but in an integer value. Yes, there is a function where you can also look in the datasheet how to calculate from this integer values the real float values. Here's you seeing our states. When I have here still error handling inside when I don't find the reader's the device ID, then I make an error handling. So first I'm checking out here, I'm settings, making a write read, setting the BNO address as first, and write there the chip ID address, which is 0, and then I read out 1 byte. And when everything went well, then I'm printing out the chip ID here. Then I sleep 1 second, so I make a break and going to the next state, the config state. The config state, I'm setting just that we are going into configuration mode, so the operation mode address we are setting, and then the operation mode config. So I'm just writing here 2 bytes. Then I'm going to the set page ID. There for safety, page ID address, I'm just writing 0, so I'm setting it to page ID 0. Next step is to set the external crystal on the on the Breakout board. So I'm setting here the sys trigger address and set there the value 80 in hex code, and write this on the I²C bus, 2 bytes again. Then I'm setting the operation mode to nRF, so again the operation mode address and 9 dimension of degree, so 9 degree of freedom. So now I have it ND 9 degree of freedom. So this is the operation mode where I get all 3 values from the gyroscope, accelerometer and magnetometer. And it calculated an internal also automatic the quaternions. In the next state we are going to read out the quaternions, and there I'm setting the address from the first value of the quaternions, from the W part, and there I read out 8 bytes then, So I write 1 byte and read out 8 bytes, and then when I get it here, I have to cast it into the quaternion values for storing it. So BNO055 quaternions in W for the part, and then I putting it together, the most significant byte and the least significant byte. Always be careful that you're using U60 cast when you're making a left shift. Then I print also out the quaternions here, and if it's the BNO is already calibrated, I'm sleeping the sensor interval and going again to the read quaternion after this interval, so this means in our case every 50 milliseconds. If not, I'm going to the read calibration, and in the read calibration I'm reading out the read calibration register, so 1 byte, and they're always splitted up the bytes to 2 bytes, 2-bit parts, and we're getting here the calibration from the magnetometer, from the acceleration, from the gyroscope, and from the system calibration. And which part is 3 is, there I made the LED off. And when everything is 3, this means buffer is all set to 1, all bits, then I'm setting calibration as true. Afterwards I'm going again to the read quaternion register state with our sensor interval. Here I'm putting all the states together, and last but not least, here I start everything. So first I'm setting the LEDs as output, making it on at the beginning, and set the initial state. And also when there was an error because termination, so the device ID I could not read out, then I'm starting it again. So I'm using the error sleep Do I still have servo sleep inside? Yeah. Okay. And when I'm building this, I can transfer it to my board and get the values out. So you're seeing here, I already transferred to this different modules, so I'm making here also sending the data directly to a second module, that I don't have any cable. And you're seeing here the LEDs are still lighting all. When I let it down, one is going out, the second one, when I'm turning around for calibration, it takes a little bit. You have really to make a little bit around, turning it upside down. It's not so important that it's so accurate, but when it's calibrated, of course, it's more accurate. But the values that we're getting already with this calibrated registers are already quite okay. So you see now all the LEDs are out, so this means the device is calibrated. And when I connect now, so you're seeing here we're getting the values, yeah, and when I'm moving it around, we're seeing that the quaternions are changing. Yes, these are still the integer values, so they have to be calculated into float values. And I do this with, this is why I'm using here UDP for sending the data to another module. Can show it to you for short. No, really careful that the right selection is made from the file. So here, so I add here actually only one state, send quaternions, yeah, and I send it to a defined IP address with the number 1 from my mesh network, from my thread network, and I'm just sending here. I'm using the sprint buffer and sending so quaternion values, yeah, to the second module which are lying here. And the second module just open a UDP port and print it then out over the UART. And when I get it there, what's quite nice is to use is Python with VPython for making a visualization, and there I designed also the board. You're seeing it's just a few lines of code for making this board, and the calculation from the values you're seeing then here, where I calculate the roll pitch. You find from quaternions to pitch and roll, you're getting also the formula in the internet, yeah. But the first thing, of course, what we have to do is to calculating the quaternions, yeah. Split it here and calculating to flow using here the scale. The scale variable is up here. So this is a formula to calculating out the quaternions out of it, yeah. And then here the function for calculating your pitch and roll. And when I start this, you're seeing here the board, and you're seeing here my board on the side, yeah. And you're seeing that with the quaternion and 20 Hertz or every 50 milliseconds, it's quite smooth, yeah. So even when I make it faster, And also the transferring with UDP and thread working here fine, so it's fast enough. I would not know how many from these modules or how fast I can really make it, but with 20 Hertz it's not a problem. The BNO055 is really quite powerful. It's a 9-axis sensor. There are other sensors out, a lot of others also I'm used. This one is a bit more expensive, but through the Fusion library you can get directly the Quaternions, and it's easy to use. And when you make around one time with Euler angles, you know the problems with the gimbal lock and also the 45 when it's more the angles than 45 degrees, and it's also not so smooth anymore. So Quaternions are really nice. I will put also a video from a link from the video from Paul McWhorter in the description. He made really a nice tutorial about the BNO055 with an Arduino, and how to calculate from the accelerometer and gyroscope sensor Euler angle. He explained it really in details. So I couldn't make it as good and not necessary when it's already out there. So take a look at this video. Like I said, the Gerber file I will put in the as download in the description if you're interested, and hope you like the videos and give it a thumbs up, and see you in the next video.